Thank you very much indeed, Peter. That's another beautiful presentation. I thoroughly enjoyed that. I love the huge simplification over the standard way of doing things we've got. I think 98% might be an underestimate there. So thank you very much indeed for that. And I'd like to throw the floor open for questions from everybody. So if you would like to jump in, put your microphone on and go for it. Shall I kick things off? Oh, sorry.
When you were talking about the P1 cross P2 in the real space, I was just wondering if that was when this is interacting in this space. Does that mean that? Can you say more about that?
Yeah, what I can say there is that's an example of the duality of the spaces. The P1 cross P2 is real space. And the other one, the E, P, and M axes are the vacuum space because they're K, I, and J. And so that's the duality. You get a single direction in both spaces. So the same information crosses over. Now, I've done quite a few examples of that in various works, how you get this crossover of information. And it must be crossover because if the fermion and the vacuum are sort of mirror images, then one must tell the other one what it's doing.
Thank you.
Okay.
Can I come in on that one and ask about because I think it's spot on with thinking about fermion, the particle itself, and the interaction with the rest of the universe being you're calling it a reflection of that. Now, I'm intending to give another talk in this series on why I think that's not quite a reflection, although that's not close to what's required, but rather an inversion of the process that's happening inside of fermion in terms of the interaction between fermion and the nearest fermion.
It isn't directly a reflection. It isn't the minus of the thing.
Yes.
If that's what you mean, it isn't that.
No, okay. You mean reflection in the sense that it's
reflecting in one axis.
Yes.
It's reflecting in a single axis, K, I, or J.
Okay, so it's a reflection between 2 points. The point of
well, you can think of this. If you can think of the parity as reflection in the space axis, so it's reflection in that axis, or it's reflection in T axis or C axis.
Okay, good.
Well, that's what I mean. It's not a total reflection. If it was a total reflection, then that would be the rest of the universe.
Yes, okay, right.
Which it can't interact with because it's not localized at the same point.
I hear what you're saying, but if we're talking about light interactions, so light speed interactions, then there is a sense in which that is local at the particle, and that they're all zero integral.
But that's what I'm saying, that is in the bracket. Outside the bracket, which is non-local, is nothing to do with the speed of light.
Okay, right.
But Pauli exclusion is immediate. It's got nothing to do with the speed of light. Well, inside the bracket, it's entirely the speed of light because it's relativistic.
Okay, righty-ho. What I'm going to talk about is that reflection or that inversion in terms of interaction, not just the Pauli exclusion principle, in a later talk.
Okay.
More questions?
I had one, if that was right. Just in terms of your dual spaces that you're mentioning, Peter, obviously you were mentioning Clifford algebras at some point, or multiple points during that, but saying that this is a sort of a dual space, and you've got your two sets of sort of vectors that are forming those spaces. Yeah. But the thing that I'd really interested to see is how you're defining products within all of this. So in the sort of Clifford algebra, geometric algebra kind of formalism, you have this kind of idea of products of vectors giving you directed areas and volumes and all that kind of stuff, which I can see that working in one space or the other in what you're talking about, but I can't get my head around what the product between vectors from
it's a commutative spaces would be. It's a commutative product. the two spaces are commutative with each other.
Yeah.
So the blue space and the red space are commutative. In effect, they don't even know of the other's existence.
Okay.
Except with the fermion.
No, the fermion is at the boundary of the two, but they don't. But it's just as far as the red space is concerned, anything blue is simply like scalar multiplication. It's commutative. It doesn't know that it exists. It's the red and the blue don't anti-commute. That is standard Clifford algebra.
Yeah.
That's
oh no, I know, but in terms of standard Clifford algebra, where you have this idea of creating geometric objects through the product, like that's the kind of interpretation of what that product operation is. I wasn't sure if there was a similar interpretation of,
no,
like you're saying they commute with one another, but if there's any like in terms of how you're generating all those elements in your 64 objects, like how that, if there was any interpretation of how that product side of it is working.
Well, it's a tensor product. Everything multiplied for everything else, and the things that are anti-commute when you multiply, and the things that are commutative commute. It's the same, it's the same as if you multiply gammas.
Yeah.
And I've written a paper about all the different versions of gamma. We had 8 different versions of how you could do the gamma algebras. Double Pauli matrices, double vectors, double vector quaternions, complexified double quaternions, and lots of versions of it. We have a paper on that
Okay.
a couple of years ago. You could probably find it on ResearchGate. I think is it on ResearchGate? Yeah.
Okay, I'll have a look. But well, I suppose
I think it says in it.
But there's not like an extension of that idea of the sort of bivector elements giving, or the quaternion elements giving you rotations, or other ones giving you Lorentz boosts and that kind of stuff. Or...
There is the same as in the standard Clifford algebra. This is exactly standard Clifford algebra. It's just that I use these symbols. So, in fact, we've recently got hold of Clifford's papers and actually looked up Clifford's original paper. And
cool.
I found that was infinitely more understandable than any presentation of Clifford algebra I've ever seen since. He knew exactly what he was talking about.
Yeah.
Unfortunately, he died so young that the subject got dropped for a long while.
Hmm.
Right.
Cool. Thank you.
More questions? Thank you.
I think the central thing that you're presenting here is the Dirac operator.
Yes.
And I'm wondering, anything that is correct me if I'm wrong, but anything that is nilpotent is essentially a condition. It's not like an equation where one side produces the other, but it represents a general condition.
Yeah, it's a general condition.
I was just wondering, could you make any comments about, my guess is that this operator is some condition on nothing, the absence of anything, but could you make some comment on that?
I think it's this idea that the boundary of a boundary is nothing. I think that's what it's really getting at. And it's, when the people say the boundary of a boundary is nothing, and I think this is the boundary of a boundary. And I think that's the sort of implication on that. But it's also, if you isolate some chunk of things and an energy conserving or energy exchanging chunk of the universe, it will always have this nilpotent condition with the rest of it. You can take that up to higher levels, because though we don't normally think of classical physics as using E squared minus P squared minus M squared equals 0, in effect it does. It's just that we don't notice it.
Can you separate that condition into the two pluses and minuses? In other words, if it's a condition on nothing, would separating it be the method for generating the positive and the negative, the two opposites? And is that I'm not sure. I might have seen that actually in your equations, but
Yeah, I think you know, that rewrite structure I have does that in a way. It starts off, it's always dual. You can never get away from the duality. That's a fundamental condition. But you can look at the aspects of it, and the thing that makes it possible is the fact that it's anti-commutative. If it weren't anti-commutative, you couldn't separate anything out. To me, all discreteness comes from anti-commutativity, because you create a kind of boxed off set of things, which is a kind of boundary. And I think that that's what's happening. That's how you can separate something out. You can only separate out something by using the anti-commutative concept. You still get nothing overall, but it separates out because, yeah, it's a discrete chunk of things. I think I need to talk about that in a different talk, really, rather than this one, because this one is assuming mathematics and so on, and the things that I didn't assume when I did that.
Coming back to the math. Coming back to the math, in the kind of algebra you have two kinds of products. You have a commutated product for the complex part of the algebra, and you have a Clifford product for the other part of the algebra. So the product in the commutative part is kind of like a real square root of real squared plus imaginary squared, whereas in the Clifford part it's the square root of time squared minus space squared, or vice versa. So one of these can go to 0. One of them, so the Clifford part is a non-division algebra, where the complex part's a division algebra. But what concerns me is that with the complex part, you can move the phase factors around, and you are modifying those phase factors, so that you can move from different classes of Clifford algebras with the same dimensions. So, for example, from CL14 to CL 50, through judicious choice of the way that you change the phase in the complex part of the product. Is that anything that does that worry you in any way in terms of this? In terms of the fact that it might still be too flexible? Now, you've chosen a particular one here, which is a very nice one and which works, but that's kind of chosen because it works rather than for any other reason. And there may be a large number of those different choices which work. So if we're moving towards a solution of Hilbert's sixth problem, there's still too much variability within the algebra to choose exactly which of the ones is appropriate in terms of describing the universe. Is that a worry?
No, it doesn't worry me at all, because it wasn't chosen because it worked. As I said, I had the algebra before I thought of applying it to Dirac. Mm-hmm. I had the algebra for a completely different reason, for the fundamental theory, and I'm going to give a talk about that sometime to another group you may join. I had these four algebras I had long before I thought of applying them to Dirac, and I had them for fundamental reasons.
I'd love to see that talk as well. Could we, I don't want you doing too much work in sort of presenting too many talks, but is there something there which we could record and stick up as well as a joint?
Yeah, well, for another group, I'm thinking of giving a different talk, which is you know, starting from a more basic level, and I will talk about that in this. But okay, good. I didn't originally set out to do the Dirac algebra at all. I just suddenly realized, well, this will work for Dirac.
Well, Mark and I had a go at some of these things and having a look at complexifying our Clifford algebra CL13, and we found that we could do anything we wanted with it. I've got something I could show you, which is up on one of my other screens at the moment. But we could move those things around anywhere, and and that comes to something else. I think there's a couple of things I'd like to do. One is to simplify things further, because I think you're absolutely right that there's far too much in the starting point of mathematics. And I think there may be a further simplification possible to decomplexify the thing. I'd like to try and do that. So to remove the complex part and just get a pure Clifford part.
Can I mention that Clifford's, if you read Clifford's paper, Clifford's view of Clifford algebra is exactly what mine is. If you it isn't complex numbers, and quaternions. It's made up of an infinite set of quaternions going to forever, and then some incomplete ones appear to be what we call complex numbers, but they're just incomplete quaternions.
Yes, I agree with that. You're right. We have a two-dimensional. Well, we have a complex numbers are a Clifford algebra. CL11 is isomorphic with complex numbers. So
yeah, but I'm saying I found other people's versions of Clifford algebras was far too complicated. If you take
I agree with you.
Clifford's version, it becomes incredibly easy. But I could do this same stuff using gamma matrices as long as I kept them as gammas, and as long as I rewrote the wave functions with gammas in them, which people never do.
Yeah, I know what you mean, but the problem Martin and I had when we looked at this stuff is that once we complexified it, we could morph different Clifford algebras or different signature Clifford algebras into one another, and we just thought that was too floppy.
Well, I've got a reason for this particular algebra, and the fact that it's two spaces is very neat.
Yeah. Mm-hmm. You mean the two quaternion spaces? I think that's incredibly neat. Is that what you mean?
Yeah, two spaces, two actual vector spaces, if you want, because you can put the complex time bit with the quaternion charge bit, and you get another vector space. And so you think two vector spaces together, and it's very neat because then your physics is just the intersection between two spaces. And Descartes wanted to make physics into space, but if you make it to two spaces or dual space, even better, dual spaces, I even call them space and anti-space.
Okay, in the Clifford decomposition we do, we have four spaces, four three spaces, and the four three spaces have different characteristics in them as well. So you end up with four superimposed three spaces, and you have this not a fractal structure but it's nonetheless a hierarchical structure of spaces. So, and that's also a very neat way of characterizing things as well.
Anyway, complex or not, you can see that it's very powerful for getting results. And I can't believe it's possible to do it really simpler.
Well, look, I think you and I are going to see if that's possible or not in this.
I think this is incredible simplification.
I agree with you. I think it's an absolute beauty, and I've been excited since the first talk of yours I heard a couple of years ago about this. And also, there's a huge amount of excitement on my side from finding somebody who's also found some of the same points where Dirac has mixed up his eyes in different. But I think I have a couple that you don't, and you have a few that I don't. So I think at some stage, what I'd love to do is sit down with you with your 4th edition copy of Dirac and my 4th edition copy of Dirac, and go through them as the bits where he's kind of been a bit vague about it. If he's going to
I think the hydrogen atom calculation, it kind of works, but it's kind of sleight of hand because it assumes that the wave function isn't a variable. It isn't variable in space.
Doesn't that worry you a little bit? Because you put
I don't do that.
You don't need it. You don't need it.
I looked at that calculation and saw that really the only thing that was changing was the phase.
Yeah. And so you're right. It doesn't matter. So the phase is a gauge transformation anyway.
But you're not entitled to say the differential is applying to this wave function.
You're right. It doesn't.
An amplitude which varies with space and time.
Yeah. No, I think you're absolutely. And I think you're absolutely spot on that. And I got that from the first time I heard this talk of yours. That was a revelation for me at the time.
Well, he gets his calculation right, but you know. I just looked at that and said that's not possible. So the only thing that's possible is to do it on the phase only.
But there is one other thing. If you put a harmonic phase in, if you chose in other words, if you did go to 2 phases, and you could choose to do that and put a relationship between the phases to 2, for example, then I think you could get a relation out there as well, because then you just have you change the operators to deal with the harmonic. Because if a phase locked with one another. So if there's a phase, one phase defining another phase, I think you'd still get a single pole operator output, even with double frequencies, like you get in the Zitterbewegung, for example. So in the Zitterbewegung, you have a doubled frequency oscillation, the Zitterbewegung oscillation, which is at twice the Compton frequency oscillation. And I think you could have that.
2 spaces.
Yeah, in 2 different spaces, exactly. In 2 different spaces. One of
Michael
them
wants to ask a question.
Yeah, good. Okay, Michael. Yes, sorry.
Yeah, thank you very much indeed, Peter. I really enjoyed that. It was utterly fascinating. I got a much better sense than I had before of how all of your stuff is coming together. I was particularly taken by the suggestion that all discreteness might ultimately be seen as coming from the anti-commutativity, having a purely algebraic origin. That was a very nice idea conceptually. I just wanted to ask one question about the kind of general Clifford algebra framework. Is there any role at all for the Bott periodicity, for the kind of eightfold periodicity that you get in the towers of Clifford algebraic structure in your framework, or is that part of the this rather over heavy mathematical superstructure that you want to get away from and just concentrate on the cleanest, simplest model?
Yeah, I mean, what I've said is that this structure looks like a broken octonion. The whole 8.
Yeah.
You start with 8 operators, so in a sense, there is a role because you can map it onto an octonion, which really is a version of doing that eightfold structure, that eightfold periodicity. So you can map it onto an octonion as long as you ignore the anti-associativity and break the octonion.
Right.
If you break an octonion by multiplying it left or right, you basically end up with something that's Dirac algebra as I understand it. But one of the term becomes a complex number effect, and two lots of 3 become quaternions. So you get a complexified double quaternion. And yeah, in a sense, that eightfold structure is present in this because I start off with 8 units.
Yeah. Yeah, so it's very interesting. You also mentioned at one point that you'd shown that Cole-Furey's approach to the octonions, that in fact she actually has the Dirac algebra there without having recognized it. Have you published anything on that? Is there a
yes, I have.
place you can refer me to for that?
2 papers which you can find on ResearchGate, one with Sydney and one with on my own. One's called fermion structures or something like that. Standard model fermion structures from something or other. And the other one's called Are Octonions Really Necessary to the Standard Model?
Ah, okay.
They're recent papers.
Okay, well, thanks.
You find them on ResearchGate.
Yeah. Lots of other things I wanted to ask about the relationship between the vacuum and the the part of the formalism within the brackets where you do get relativistic structure, but I don't think I've got them sufficiently clear in my head yet. So we'll correspond further about this. But thanks again for a great talk.
Thanks, Mike.
Peter, could you talk a little bit about quark confinement in relation to your model?
Okay. Essentially, to me, quark confinement is really vectors. It's saying that you can't separate out the 3 vectors of space. It's really space rotation symmetry. So we can't separate out px, py, and pz because it's the what you call it, the what's the name for that thing? The affine structure. It's part of the affine structure of space. And to me, that's why you get quark confinement. But I can actually derive quark confinement. I can derive it by what I see is that you've got those 3 structures, px, py, pz, and it's like as if they rotate between the 3 axes, but the 3 nilpotent structures. They rotate between the 3 brackets, and if you look at the rate of change of momentum is going to be a constant if it's a non-local process, which means you've got a constant force, you've got an energy proportional to R, and so you need to express that locally, we're saying how non-local affects local. So to express the non-local concept locally, you need to put in a potential proportional to R. Now, when I did that and solved it, I got a solution looking very like the strong interaction with infrared slavery and ultraviolet freedom. But I couldn't do that today. I didn't have the time.
And what do results like scattering from a proton and seeming to give give credence to the existence of subconstituents mean from your point of view?
Well, that's what it means. It means that when you tie that quaternion I to the ijk of the vector, you're actually changing its character locally. So it has to bring in those vector properties when it does it. You can't ignore the vector properties. So you've got to bring in the vector properties, and you've got to bring in rotation, symmetry, and affine, nature and all that. So so that's what it means to me. I don't believe it has to be. I think probably that you can get hot QCD as well with it probably will apply to hot QCD as well. Probably the quarks can be connected to more than one particle at a time. Well, they are anyway in a nucleus. Otherwise, there wouldn't be any strong interaction holding the nucleus together. Quark isn't only. It also has properties relating to other quarks in other protons and neutrons.
Thank you.
Peter, your calculus is based on the principle of nilpotence, to the nilpotence of the operator product with the vector, and connecting the vector and itself and the operator to the wave function via the properties of the wave function. So beautiful. Should you be calling that a principle of nilpotence?
I mean, it certainly could be called that, yes.
Okay, right. Because I think that's where you're putting in your physics, as it were, by saying that these things have to square to zero. So that's the point where you're really putting in the physics of this thing.
That's the point where I actually branch out from conventional theory and find something completely different.
Yes, it is your core. It is therefore your core constraint, and I would think that would really need to be put in as a principle, as something which you're taking as a starting point and then working from there.
Well, so, I bring it in about halfway through when I say that I'm going to now say that every possible fermion wave function is a nilpotent.
Nilpotent, yes.
That's when I bring it in. I'm going to bring it in when the occasion demands it. And let's say at that point, I'm now going to branch off. I'm now going to say this, which is not normally said.
You're right, it isn't. But does it worry you at all, the fact that when you do that, the mass doesn't affect the dynamics, that the mass is only brought in to provide that nilpotence through a term in the wave function? That you need to have it to balance it, but it merely comes in as a balancing function for your nilpotence. It can be any number, of course.
Well, that suits me because the mass only comes out of the Zitterbewegung anyway, and out of the balance between two spaces. If you wanted to say the creation operator and the annihilation operator are completely cancel each other, then the only good way to do that mathematically is to do it using that discrete differential that I did, because that will then make the operators completely cancel. If they're positive E and positive B and negative E and negative B and so on. But that's the only thing that makes them all cancel. But normally the mass doesn't cancel because that's the one that's created at the point where the particle's created.
Aha. Do you have any view on how that mass, for example, is coupled to the charge that's generated in an electron?
I have had actually some speculations about how to derive masses of particles, and I've got quite a number of those. I mean, how good I'm far more certain about this work than I am about that, but I have a number if you want to have a look at them, and if you've got others, we can exchange ideas on that.
I've done the same sort of thing. I've tried to calculate masses, and I've got some things that they're okay, but they're flaky in places. They're all over the place.
Yeah.
And there are some relations that look nice. We should compare notes on that one at some point.
Yeah, because I think maybe if we put the ideas together, we might get something better than either of us have done alone. I certainly think that I've got some ideas that might well work for that, but others I'm not sure of.
Yeah, me too. You and me both.
I wouldn't put that in this talk because I think it's too speculative.
No. I'm loath to talk about mine as well for the same reason. Good. Anyway, more questions.
Wolfgang here again. Peter, I noticed on one of the slides you mentioned simply multiplying a nilpotent by IH and getting a quantum equation, or that was a simple way of going from your formulation to quantum. And I just wondered, I've always, from a very physical point of view, assumed that the H is some kind of a scale factor that that kind of divides the area where reductionism works to one where it no longer works. And I think it's an important physical. And I just wondered, is there multiplying a 0 or a nilpotent by IH doesn't feel very convincing. Is there a scale factor that inside those equations that would take the role of a Planck's constant?
Yeah, there is in the amplitude term. The amplitude term always includes that. You know, if you're doing quantum, the amplitude terms always includes that. It's just the operator term that I put it in on the outside, but the amplitude term always includes it. So it's still there. It's just that it's a neat way of doing something that's difficult normally, because you know, it's difficult to justify including that factor normally. But in this particular case, on the operator, I didn't need to. But it is there in the amplitude term anyway, as the max as well.
All right, thank you.
More questions? Well, I think on this talk there's been so much interest that what I'd suggest is that if anyone has any other questions to pass through to Peter, that they... Oh, hello, Pete.
Yeah, I was interested in one of the summary things that Peter provided, which was the you mentioned mass being manifested through the gluon field with the Higgs field or something like that. And I was wondering, how can that be with electrons?
I'm not sure I said that. I think I said that mass came from the I was talking about the Higgs field. I was talking about that wasn't about electrons. That was about
protons.
Protons, yes.
Right.
I'm saying well, the mass for the proton, but I'm saying that because that process doesn't happen in electrons.
So how do you get mass with the inner?
Well, we already know how to get mass in electrons, because the mass of the electrons is done by the Higgs mechanism and using the Yukawa potential. So the Higgs mechanism for creating W and Z and so on can be applied to a Yukawa potential way of getting it from electrons and other fermions, but it doesn't normally apply to protons. So the electron mass effectively comes from the bulk of the electron mass comes from the fact that, well, the electron mass comes from the fact that it's partially left-handed and partially right-handed. But so if you got left-handed and right-handed, you always get mass because of switching between them. Now, normally that's considered an aspect of the Higgs mechanism, and you can do that, as I say, using the Yukawa potential for electrons. And the reason why electrons are easy to give a mass to is because normally a particle can't interact weakly if it's right-handed. It can only interact weakly if it's left-handed, but it can interact through the electric interaction if it's right-handed. So the right-handed bit of the electron, which interacts through the electrical interaction, will give it mass. But in the case of the proton, though there might be a bit of mass because the proton might be charged, the general feeling was that it was the gluon exchange that caused the mass, and that wasn't a Higgs mechanism. But I say, yes, the gluon exchange is the energy of the gluon exchange is the same as the mass, but the mass is that energy of the gluon exchange couldn't happen if the symmetry didn't work and the proton wasn't both right and left-handed at the same time. And so therefore that aspect is a Higgs mechanism aspect. Does that make sense to you?
Not terribly. I've been trying to follow John's work for the last few years. Have you read his papers?
I've read some of them, yeah.
So what is the intersection between John's work and your work?
Well, we need to discuss that between us to find out. We haven't been able to sit down and do that because of this. We were going to do that this summer, weren't we, in August in Cambridge and Scotland, and we were going to have meetings. But we know that we have some things that we can talk about and some commonalities and some differences. So we need to get down together. And until I can say, well, what do you mean by that? And he can say to me, what do I mean by that? Then we can't really do it. So I can't give you a complete answer at the moment.
Did you find areas in John's papers that you thought were wrong?
Well, as for at the moment, yeah, there's things that we could actually maybe do some joint work on. That's certainly possible.
Yeah, I'm looking forward to that process as well. We were actually we did, before the coronavirus started, try to look for a window to work together. Maybe in spring of this year, but spring of this year is sprung, so that's the end of that one. And
yeah,
well, hopefully find a window.
We had a difficulty because of Martin's condition. John couldn't spare.
That's also true. Yeah.
And so we couldn't spare the time earlier. And then now the world situation has screwed us up. And we can talk over this mechanism, but it's much easier, talking face to face.
I think I was aware of Peter. I didn't know Peter was Peter. I'd referred to at least one of his papers in the past. But the first time we really met was 2 years ago. So we haven't had a good, well, maybe Liège will happen, who knows, but we haven't really had a proper session face to face to be able to go through some of these things.
We both noticed the same fault in Dirac anyway.
Yeah, so we have commonality in seeing problems in that area. And also there's some big similarities between the kind of way we think about things, and that Peter uses Newtonian algebras, which are subalgebra, and he uses Dirac algebras, which we have in common. And then he complexifies Dirac algebras, which I think is a problem. But then he thinks there are problems with some of the things that I'm doing as well in terms of the connection I'm making. And we just need to go through and have a lot of discussions and take things forward in a lot of different fronts. And we'll both learn something from that with a bit of luck.
Sydney wants to ask a question.
Yeah. Okay, so I was just going to ask Peter, since we live and observe, quote unquote, in the blue vector space.
Yeah.
In some way, can you say a little bit more about how the observables of the algebraic operators in the red vector space, how physicists can know things about that given the medium through the blue vector space, if that makes sense?
Okay. What I'm saying is that non-local events affect local ones, affect local structures, non-local things. So I gave an example with Pauli exclusion is a non-local thing. That's due to the red vector space, and that manifests itself by a potential in the blue vector space. That we don't observe the potential, but we observe the effects of space and time changes, because the operator changes. That changes the phase which is in the red vector space, but that then gives us a nilpotent amplitude, and we can actually calculate things if we can get them down to the level of space. Okay, so we can always do that. But space has always been the only method of observation of anything. So if we measure time, it's always through some repeated variation in space of some kind, even if we don't see that, even if it's counted automatically, that's how we measure time. And of course, mass or charge, we can only measure by what happens to an object in space. And some things we can't observe at all direct. We couldn't observe a charge if there weren't another one. We can only observe that as a squared interaction.
So you're saying the antisymmetric wave function is kind of when we had the blue space and the blue vector space and the red one, and you had the antisymmetric wave function.
Yeah.
That was an indicator that something was going on in the red vacuum space through the nilpotency of the.
Can people hear you? Can people hear you?
Yeah, we can hear her. Yeah.
Yeah.
That's all I was asking, was just.
Yeah, that's correct. It's an indication that we can observe in one space what we can't observe in the other, but we know must take place. There's a kind of hidden space which changes things in the one that we can observe.
I think that an observation always boils down to some sort of energy exchange. Some piece of energy here interacts with something somewhere else, and there's a spatial relationship between those, and they take place along. Well, they appear at 2 points, and you can draw a line between 2 points. So they then appear along the line. In the sense that that line then defines space, yes, we can only measure things in space in terms of a matrix of space we have. But the things that we measure are actually scalar events. Their energy vanishes here and then reappears over here, the energy exchange, or photon exchange, or motor exchange. But there's some sense in which the spaces which we're interacting with are many different spaces. And the extra space, so if you feel the table, that space is really what you feel on the table. It's not space in your fingers, but it's an electric field space that you're touching there. But that electric field space is itself mapped onto space, because it has a matrix of those things, which is the spacing of the way that the vector position of those things with respect to one another defined. So what you feel is energy exchange. What you touch is energy exchange that is mediated through field space, but then is mapped onto space. So they're projections. I'm going to talk about this in a later talk in terms of the way that space arises out of different spaces and is all mapped onto space. So I hope to expand on this.
So what you might call local spaces.
Yes. And what is locality? And because there's more than one kind of... Locality is often misunderstood as being something which has to be close by in space. But that's a too simple way of describing locality. Locality, for a observing human, is the entire light code of interactions that you have. Everything is local to you that hits you at this summum of space and time which we happen to be at, each one of us, at the present moment. And it's with respect to that we, individuals, measure everything. With respect to the observer, our rulers, our clocks, things that we measure things with, what it looks like. How does it feel to you? You know, what's your space? And that's our own space. And each of our spaces, in a sense, individual, the observer's space. I think this is something which Wolf has emphasized quite a lot as well, and I'm 100% with him on that. This is a very important part of the space. The space we live in is our own space. I don't know if that helps or mystifies, but I'm going to talk quite a lot about that in a future talk.
Yeah, I certainly think we live in a local space, and each local space is a different local space. But yeah, okay.
Peter, I think I'd like to draw this set of questions to a close now, unless anyone else has got a burning question. That was a superb talk. Thank you very much indeed for sharing it with us and for dealing with a lot of questions at the end of it as well. That was quite a marathon session. But can I suggest to everybody, if there are further questions, that you could send them directly to Peter, of course, if they're private. But if you could send them to me, then we could maybe have another point at which we could put other questions to Peter if we get an interesting set of them. So there may be a bunch of questions that would be interesting for the whole group. So if you could feed them, copy them to Peter and to me, for example, and we'll maybe arrange another session if Peter thinks that's up to you there. But if you think there's a bunch of interesting ones you'd like to answer, perhaps you'd like to come on video for a few minutes and just say, "Oh, this works like that," or whatever, and sort a few things out. So if anyone wants to stick those up in general, that would be absolutely brilliant. It's a way we're trying to do things in the future as well. Maybe have some talks where people put in questions, and then we can, because you know, this is things like on the spot. If people are asking a bunch of questions, quite often there's a misunderstanding between the questioner and the answerer. So things kind of miss And then you think, oh, that's what they meant. Oh, that's what they meant. So if we can get around that, and you too, Peter, if you've got anything where you think, oh, I didn't do that right, or if you think that was a stupid question because, or is it what you're really asking with something else, then you can put those things in as well, and we'll attach them in some way, shape, or form to the discussion around this. But thank you, ladies and gentlemen, all of you, for your time on a Sunday, different times on a Sunday. There'll be, well, you're saying originally you might need to do 2 of these sessions. Are you happy for the time being, Peter, or do you want to?
I'm okay for the time being. I might need to do another one later, but for the time being, I'm okay. And I might do a more elementary one because I'm doing that for another group. So
Well, what you could do, and what we are doing, is sticking some of our other work, rather than repeating it twice, we're recording it and then stick it up as an associated video if it's interesting. We can just point to, we've got another YouTube channel where it's up, we can just point to that, and then the whole thing just ties together. So and people can comment on that too, or watch that too. So feel free to do it whichever way you want to. Good,
okay,
good.
all the best.
Yep, cheers. Right, go, everybody. Take care. We'll see you same time, same place next week. There'll be another talk coming up.